Welcome to the Knowledge Science Pulse podcast, where we dive into the latest advancements in artificial intelligence. I'm your host, Sigurd, and today I'm joined by my co-host, Carsten. We have two exciting papers to discuss that shed light on how large language models can be transformed into powerful text encoders, and how hyper-detailed image descriptions can unlock new possibilities in vision language model.
That's right, Sigurd. The first paper, LLM2Vec, Large Language Models Are Secretly Powerful Text Encoders, introduces a simple unsupervised approach that can transform any decoder-only LLM into a strong text encoder. They call it LLM2Vec, and it consists of three simple steps, enabling bidirectional attention, masked next token prediction, and unsupervised contrastive learning.
Fascinating. Can you explain what each of these steps does?
Sure. Enabling bidirectional attention allows each token to access every other token in the sequence, overcoming the limitations of causal attention. Masked next token prediction adapts the model to use this bidirectional attention by training it to predict masked tokens based on both past and future contexts. Finally, unsupervised contrastive learning is applied to learn better sequence representations.
And how effective is LLM2Vec in practice?
The authors applied LLM2Vec to three popular LMS, ranging from 1.3b to 7b parameters, and evaluated the transformed models on English word and sequence-level tasks. They outperformed encoder-only models by a large margin on word-level tasks and reached a new, unsupervised state-of-the-art performance on the massive text embeddings benchmark, NTB.
That's impressive. When combined with supervised contrastive learning, did they achieve even better results?
Yes, they achieved state-of-the-art performance on NTB among models that train only on publicly available data.
Moving on to the second paper, ImageInWords, Unlocking Hyper-Detailed Image Descriptions. It tackles the challenge of creating accurate and hyper-detailed image descriptions for training vision language models. What's the main issue with current datasets?
Current datasets typically have web scrape descriptions that are short, low granularity, and often contain details unrelated to the visual content. As a result, models trained on such data generate descriptions replete with missing information, visual inconsistencies, and hallucinations.
So how does ImageInWords address these issues?
The authors introduce a carefully designed human-in-the-loop annotation framework called ImageInWords, QW for curating hyper-detailed image descriptions. The framework combines the irreplaceable quality of human annotators with seeded metadata from machine generations.
Can you walk us through the process?
Sure. It begins with object detectors, identifying individual object instances in the image. Then, a vision language model generates granular captions for each detected object, which seed the human annotation process. Data workers augment and fix the object-level captions to make them richer and hallucination-free. Next, at the image level, an image caption is generated by the vision language model to seed the final image description. Crowd workers consume the image-level seed captions along with the object-level human annotations to fill in contextual gaps.
That's a thorough process. How does the resulting TUW dataset compare to other dense description datasets?
TUW contains more information along multiple dimensions. The descriptions have an average of 9.8 sentences and 52.5 nouns, 28 adjectives, 5 adverbs, and 19.1 verbs per description. In side-by-side human evaluations against descriptions from human-generated datasets and GPT-4v outputs, TUW descriptions were rated as more comprehensive, specific, and human-like, containing fewer hallucinations and better leading sentences.
And how well do models fine-tuned with TUW data perform?
Models fine-tuned with TUW data excel by 31% against prior work in human evaluation dimensions. The authors also evaluated text-to-image generation and vision language reasoning. They found that their models' descriptions can generate images closest to the original, and they produce more compositionally rich descriptions, outperforming the best baseline by up to 6% on various datasets.
Wow, these two papers show the incredible potential pushing the boundaries in both language models and vision language models. LLM2Vec demonstrates that decoder-only LLMs can be transformed into powerful text encoders, while ImageInWords highlights the importance of hyper-detailed image descriptions in advancing vision language research and application.
Absolutely. The level of detail attained in the TUW annotations can help generate better descriptions for text-to-image models and aid in applications for people with visual impairments. It's exciting to see how these advancements can contribute to the future of AI.
Indeed. Thanks for joining me today, Carsten. And thanks to our listeners for tuning in. Stay curious, and we'll be back with more cutting-edge AI research in the next episode of Knowledge Science Pulse.